The relativistic Doppler effect. Now the question I would like to address is what happens if the source of waves and the observer are moving relative to each other with a speed close to the speed of light so that relativistic corrections become important. So if a wave source and an observer are approaching each other with a relative speed v, the frequency f prime measured by the observer was given using Galilean relativity by the following arguments. For example, if the source is approaching the observer is at rest, we would see that the wavelength of the waves that are approaching the observer at rest would seem to decrease. So by how much? Because every time a maximum is emitted, we will have the source move by an amount v source times the period before the next maximum is emitted. So we would see that there would be a decrease in the wavelength. So the actual wavelength lambda minus delta lambda would be the new wavelength detected by the observer at rest. Now, what is the wavelength detected by the observer? Because the observer does not see a change in the speed of the waves, propagation speed of the waves, it would be the propagation speed divided by the frequency detected by the observer. So what do we expect to see? The frequency, the detected frequency, to increase as the source is approaching the observer. Lambda is the speed of the waves divided by the true frequency of the source minus the decrease in the wavelength is due to the speed of the source multiplied by the period, or speed of the source divided by the frequency. So with that, we see f prime is equal to f times the speed of the waves, propagation speed, divided by propagation speed of the waves minus the propagation speed of the source. As you can see, as the propagation speed of the source increases, the source is approaching the observer more quickly, the detected frequency is going to increase because this factor will decrease, so 1 over 0 is infinite. So in that limit, when the speed of the source is equal to the speed of the wave, this would be approaching infinity, right? So we would see that the source approaching the observer makes the observer detect a higher frequency than the frequency of the source. On the other hand, if the observer is approaching the source, now we see a change in the detected propagation speed of the waves, because the Galilean transformation tells us that when the observer was at rest, the waves were propagating with a detected speed Vw, because the observer is moving relative to the source by a speed V observer towards the source, the detected propagation speed would become Vw plus Vo. So the new speed V prime detected by the observer would be the speed of the, or Vw prime we can say, the actual speed, propagation speed Vw plus V0. Okay, so but there is no change in the detected wavelength, so wavelength is the same. So lambda times f prime, the detected frequency, is lambda times f, the speed of the propagation speed of the waves, plus v0. And what do we expect? The detected frequency to increase here. So f prime will be f plus v0 over lambda, where lambda is the propagation speed of the waves divided by the frequency. So we see that f prime is f times 1 plus v0 over vw. So we can see that it will be Vw plus V0 over Vw, and therefore as the speed of the observer increases, the detected frequency will increase as expected. Alright, so that was the source approaching an observer at rest and the observer approaching a source at rest. Now, when the both source and the observer are approaching each other, we will have the detected frequency to be f prime equals f times VW plus V observer divided by VW minus V source. So as the observer speed increases, the detected frequency increases. As the source speed increases, the detected frequency increases. So when they are approaching each other. Now, how should we correct this if we have relativistic speeds? Now, with relativistic correction, the detected frequency becomes f times, instead of Vw plus V0, square root of 1 plus V over C divided by square root of 1 minus V over C, where V is the relative speed of the observer and the source. So it's the speed of the source with respect to the observer, or vice versa. So this is going to be our new detected frequency. Now, when the relative speed of the observer with respect to the source, for example, increases, you would see an increase in the frequency when it's according to this, but it also depends on whether the source is moving or not. So if the source is at rest, then we would see that this would be an increase. So the relativistically corrected version of this frequency is now basically given by this new expression. So how does this tell us anything about the universe? Well, if you look at light emitted by atoms from far galaxies, they get redshifted. So the detected frequency decreases. So if the detected frequency increases, we call it blue shifted. If it decreases, it gets red shifted. So since the f prime is decreasing, we can see that this is not the scenario here where the source and observer are approaching each other. The scenario is the universe is expanding. So we would have a minus sign here and a plus sign here. So the detected frequency would be decreasing. It would get redshifted. Edwin Hubble, 1889-1953. Okay. So that this was determined using the Hubble, Edwin Hubble. So we talked about the Doppler effect. The Doppler effect results in a decrease in the detected wavelength when the source is approaching the observer. It results in an increased propagation speed of the waves as detected by an observer approaching a source at rest. And when these two are approaching each other, we will have the speed of the wave plus the speed of the observer divided by the speed of the wave minus the speed of the source multiplied by f, giving us f prime. And this scenario results in an increase in the detected frequency. And with relativity, when the source and observer are approaching each other with a relative speed v, we will see an increase in the detected frequency, 1 square root of 1 plus v over c divided by square root 1 minus v over c times f. So this is the scenario when the source and the observer are approaching each other. So that is the correct, relativistically corrected version of the Doppler effect. Now, but what we see in the universe is that the light coming from atoms, emitted by atoms from far galaxies, seem to get redshifted. So instead of an increase in the frequency, we see a decrease in the frequency. So that means the source and observer are moving away from each other. Then we would have square root of 1 minus v over c divided by square root of 1 plus v over c. And this redshift and a decrease in the detected frequency tells us that the universe is expanding.